Okay, so good afternoon, everyone. It's a great pleasure to have a speaker, our next speaker, Luke Postle, who probably doesn't need introduction. Luke obtained his PhD degree at Georgia Tech, and then immediately after or during the time, he became already worldwide known as an expert in graph theory. Luke got many prizes. Among them is Coxeter James Prize, Canadian Research Chair, and Early Career Researcher Award. And today we will have a pleasure to listen about his results on combinatorial designs.
Thank you, everyone, for coming. So today I'm going to be talking about combinatorial design theory, in particular, our new method of refined absorption, and how this will give a new proof of the existence conjecture. This is joint work with Michelle Delcourt, who's here. So I think this is really lovely. We have to talk about what designs are. So these old fundamental objects arising sort of in set theory that are very symmetric. So there's what's called a Steiner system. What is a Steiner system? Well, let n greater than equal q greater than r greater than equal 1 be integers. An NQR Steiner system is a set S of q subsets of an n set V, such that every R subset of V is contained in exactly one Q set in S. So sort of, can you find this set of Q sets where every R set is in exactly one of this highly symmetric object? And it's not clear that these should exist or anything, but if they did, it would be lovely. An N32 Steiner system is known as a Steiner triple system. And why is that? Well, here's a picture of one. This is the phonoplane. And the idea is that the lines of the phonoplane are three sets, and every pair of points is exactly one, where this circle is also a line. And so that's a 732 Steiner system, Steiner triple system. And Kirkman proved in 1847 that there exists an N32 Steiner system if and only if n is congruent to 1 or 3 mod 6. So we characterized this. And he actually did it before Steiner even posed the thing. So actually they should be called Kirkman systems. But Kirkman asked if a more general question was true. And then Steiner's like, what about this easier one? Well, actually, Kirkman already had proved it. So what can you do more generally? Those are Steiner systems. More generally in design theory, people study what are called designs, which is a similar concept, but adds an additional parameter lambda. So you have a set of S of Q subsets of an n set X, and every R set is in exactly lambda elements. And you might think, why isn't this just trivially following from the lambda equal 1 cases? This has to be a set and not a multi-set. So you can't just take lambda copies of your Q sets. You'd actually need disjoint Q sets that cover the R. So it's harder to actually do this, but sort of fundamentally the lambda equal 1 cases is actually the hardest of all the cases. And so let me tell you a little bit about the history of design theory. So again, this is dating back to the 1800s, mid-1800s, very classical. And the natural question is, for what NQR lambda does there exist this design? So what do we need to be true? What parameters can we get this highly symmetric object? And it turns out there's obvious necessary divisibility conditions. So namely, it turns out that Q minus I choose R minus I has to divide lambda times n minus I choose R minus I for all I between 0 and R minus 1. So what is this saying is, so for example, for I equal 1, if you look at one element, you can say, well, it'll be in Q minus 1 choose R minus 1 of these Q sets in a particular one. And then how many would you need to be divisible? Well, it would be in lambda times this number. So it's like if you just look at every set of size I, then it'll be in this many in a Q set, and then we'll need this many overall. So it's the obvious necessary of it. We definitely need this. And the question is, is this enough? So we'll say that n is admissible, just for shorthand, if it satisfies these. And then there's what's called the existence conjecture. So this notorious conjecture from the mid-1800s, which is the purpose of the talk, is that these things should exist. So for all integers q greater than r greater than 1 and lambda greater than 1, and all sufficiently large n, so once you fix these, there's some n large enough that whenever n is admissible, there exists a design. So this is the existence conjecture for combinatorial designs. It was sort of made by the various authors, Steiner, Kirkman, etc., kind of put this together and said, so it's not attributed to one person, but it's this notorious conjecture. And what's known about it is it has a history over the years. So I'll just mention a few key results. So in the early 1960s, Hanani proved it when Q and R are 4 and 2, 4 and 3, and 5 and 2. So again, the 3-2 was settled by Kirkman in 1847. It took almost more than 100 years to settle these cases. Then impressively, Wilson in the 1970s made this major breakthrough in design theory and showed the existence conjecture is true for R equal 2 and all Q. Right? So settled all of these cases sort of with a nice combination of recursive constructions and algebraic ones for prime powers. And it was a real breakthrough. Meanwhile, Rodel in 1985 settled what was the Erdős-Hanani conjecture. So Erdős and Hanani in the 60s asked, this seems really hard, let's make it easier. Can you sort of get an almost design or an almost Steiner system? So for example, here Rodel's implies you can get a design, but I mean that everything's in at most one set and you cover at least 1 minus little o1, the number you'd want. So you can cover almost all the R sets, but not all of them. And this was using the Nibble method, which has also been influential in combinatorics for edge coloring and vertex coloring, etc. But so that was nice. But to put a clear on what the state of the things is, until 2014, so just 10 years ago, no NQR Steiner system was known for any R greater than 5. So people did things for sort of larger lambda, but for R greater than 5, lambda equal 1, nobody knew any construction at all, algebraic anything, of an NQR Steiner system. So it seemed very far away from proving this. And what happened in 2014 is that Keevash proved it. So he showed that the existence conjecture is true. And what method did he use is he invented this method of randomized algebraic constructions. So I won't talk too much about that, but sort of randomly choosing matrices over finite fields is at the basis, and then there's a lot of other clever ideas. Just 2 years later, Glock, Kühn, Low, and Osthus in 2016 gave a second proof of the existence conjecture. This has now been published as of 2023 in Memoirs of the AMS. And they used an entirely different method, the method of iterative absorption, which had been developed first to work for Hamilton cycle problems, and then was applied to designs, and then finally used to prove the existence conjecture. So now there are 2 known proofs here, very different proofs. So existence conjecture is true. Let me tell you about the commonalities of the proofs. So let me tell you about absorption. If you haven't heard about absorption, absorption is great. It's magical. It's a fundamental technique that can be used to solve many different things, not just the existence conjecture. What is it? Well, before I do that, I need to translate the Steiner system problem away from sets into graph theory. So a lot of you are graph theorists, you'll like this. Here's graph theory. So we let KQR denote the complete R uniform hypergraph on Q vertices. So when R is 2, this is your normal KQ, but you have hypergraphs. They can be R uniform, so where all the sets have size R, and a KQR is this complete one. And a KQR decomposition of a hypergraph G is just a decomposition of the edges into copies of KQR. So you want to decompose into hypercliques. And the point is, an NQR Steiner system is exactly equivalent to a KQR decomposition of the complete graph KNR. And this might generally raise the question of when is it true that we could decompose things that aren't complete? And it turns out you can figure out what the divisibility condition should be with the following definition. So for a hypergraph G and a subset S of the vertices, you can kind of look at what's called the link graph of S. And that's where you delete the vertices of S from the vertices, and take the edges that contain S and delete the bits of S. So it's sort of like this projected neighborhood. And the point is, the divisibility condition generalizes. Generally, a hypergraph G is called KQR divisible if this number divides the size of the links for any set S. So that's sort of the analogy. So then n being admissible was k and r being kqr divisible. Okay, so now that I've talked about that, I can get back to absorption. So what is this absorption method? Here it is at a high level. It's a method for turning almost decompositions into complete decompositions. How do you do it? By setting aside beforehand a magical thing called an absorber that's capable of decomposing any possible leftover. So Rodel tells us we can get an almost decomposition. There's some leftover uncovered edges. So there's this absorption method that says I can first build an absorber that can absorb anything. So how does this work? I should mention this method was popularized by Rodel, Rudzinski, and Semrety around 2008 in a couple of papers, and now has been used widely. So there's dozens, maybe even 100 papers using the absorption method. So what is it in this case? We'll let L be a KQR divisible hypergraph. A hypergraph A is a KQR absorber for L. If it's sort of nice to include the condition that the vertices of L are an independent set inside of A. And the key thing is that both A and L union A admit KQR decompositions. So what is this saying is A by itself has a decomposition, so you can just leave it to its own devices. But if I wanted to decompose L, I could throw it at A, and L union A would be promised to have a decomposition. So A can really absorb L, on or off. It can choose. And from this, I should say then, absorbers are known to exist, and this was also done by Glock, Kühn, and Osthus in their paper. So they gave maybe a 10-page construction showing that absorbers exist. So it's kind of technical and intricate and very clever, but also uses the existence conjecture inductively on uniformity as well. But they were able to show that absorbers exist. So in the graph case, when R is 2, you can just sort of draw them. In higher levels, they get complicated. So, okay, what good are absorbers? Well, absorption method powers both proofs. So Keevash doesn't exactly use absorbers as defined there, but he still uses absorption. He still wants a magical object that can absorb leftovers. Glock, Kühn, and Osthus directly use absorbers, and I'll talk about that. But let me compare the two proofs. So what's the differences between the proof? Which are they good for? So I won't make a pros and cons list, because it's not nice to make cons, but let me tell you pros of the two. So pro for Keevash is his is algebraic. And why is this a pro? Is that generalizes to other more algebraic settings. So for example, there's things called partite decompositions, resolvable decompositions. Maybe you want to do things over finite fields and subspaces, very algebraic settings, and sort of being more algebraic would be good for these settings. Maybe you can generalize the ideas. And he does. He has a Designs too, which does a lot of these things. And more recently, with Salansani, he did this one. Another benefit of Keevash is it's one step. He sort of builds one magical super absorbing structure algebraically, and so sort of conceptually it does it more at once. There's a lot that goes into it, but that has benefits. In particular, this means that sometimes his proof gives better parameters for things like typicality and for thresholds and other things. He gives nicer numbers than you would get from iterabsorption. Iterabsorption, meanwhile, what are its pros? Is it's purely combinatorial. So if you don't like algebra, well, it's purely combinatorial, except for one little algebra bit in the middle. And that's good because it's useful for less algebraic settings. So for example, there's these things called high-girth designs I talked about in the fall, and those sort of algebra is not good for, because algebraic constructions might not naturally lead to high girth. And it's also sort of a flexible approach with its use of absorbers. By using these absorbers, you could think for other types of problems, minimum degree, things like that, that maybe you could just take this idea, I already have absorbers, and sort of change the proof a bit to do what you want. And this then sometimes gives better parameters. So in particular for the minimum degree version of the existence conjecture, they get better bounds than Keevash does. So there's some comparison between the two. Let me talk a little bit more about these. So I won't tell you about Keevash's, because it's sort of this algebraic matrix, randomized algebraic construction thing. Let me get into iterabsorption, because it'll be useful for comparison for our new proof. So what is the idea is we're going to iteratively reduce down the location of a possible leftover into a set for which we have set aside absorbers for each possible leftover. And the idea with here is they fix what's called a vertex vortex. So they start with all the vertices, and they sort of choose a random subset v1 inside, then v2, all the way down to vk, which we'll call x. And here you can just imagine, which they can do it this way, that sort of the sizes are, this is epsilon times the previous size for some well-chosen epsilon. And you can imagine that x has constant size if you want. And what's the trick then is GKLO will embed private KQR absorbers for all the possible leftovers. So what does it mean? Well, there's at most x to the r edges in a set x. You can think, worst case, either of them is in or out. So there's at most 2 to the x to the r possible leftovers. I said absorbers exist from their theorem, so just sort of embed them sort of vertex disjointly out into, maybe even this set way out here. Okay, so that's what they do. Except I haven't skipped a thing, is how do you force the leftover into x? So if we could get it all the way down to x, then the absorbers do their magic work. But how can you actually force leftover? Well, this is their nice idea called cover down. How does it work? It's a procedure for decomposing vi such that the remaining leftover is in vi plus 1. How do you do this? Well, I'm going to have a picture on the next slide, but let me say at a high level how it works. So basically, you'll randomly set aside a small proportion of edges with at least one vertex in vi plus 1 as some sort of reservoir. And then sort of for the edges that are purely inside, that don't use any of vi plus 1, you'll run nibble. That covers most of them. And then you'll decompose the leftover with the reservoir. The issue is that there are edges with some vertices outside vi plus 1 and some inside. We need to decompose this. And this you need to do with sort of induction on the uniformity of the existence conjecture. And I should mention this because I won't mention it really anywhere else. Important to this procedure, in particular nibble, is regularity boosting. So when you eat some from the next set, you have to boost back up the regularity to apply nibble again. So I won't get into that, but they did it. It's a couple-page proof. It's very nice. It uses fractional decompositions. And we're going to need that as well. So here's a picture of cover down, just in the triangle case. So in q equals 3 and r equal 2, we're doing graphs. We're doing triangle decompositions. What does this look like? Well, you run nibble on the edges outside of here, and there might be some leftover blue edges here that are purely outside. I need to put these into triangles. So I'll just sort of decompose with the random reserve I chose from here, this reservoir, and put them into these triangles. Okay, check. That all works nicely. The issue is now this vertex will have leftover edges to vi plus 1. And I have to cover all of these. So I'll have to cover all of these green edges. And how can I do that? Well, to make triangles with them, I need to put in edges here. I need to make the bases. And what problem does that become? Well, that means that you generally would be finding a kq minus 1, r minus 1 decomposition in V's neighborhood. So here it's a k21, which is also known as a perfect matching. And so you want to put in this perfect matching there. So you can do that. And then more generally, if you have sort of know the existence conjecture inductively for sort of min-degree versions, you can do this as well. And you have to make sure all these choices for all the different V, of course, are disjoint. So there's a lot of work that goes into it. I mean, basically, for the existence proof, cover down takes almost 30 pages. It's long. It's technical. This picture is a lie, yes. But if you want to think that's what's going to happen, sure. And the point is, when we do a similar thing later, which we'll call refine down, it turns out they'll have a lot of analogies to cover down. So I wanted to give you this picture so we can talk about the difference. Okay, so that was all the previous history, what was known in design theory, the two known proofs, and then where do we come in? What do we want to do? Well, let me tell you about a dream we had. So here's the dream. There'll be 3 dreams, actually. So dream number 1. Does there exist a one-step combinatorial proof of existence? So Keevash's is morally one step. You can see with the vertex cover down, the combinatorial one is not. Could we find a one-step combinatorial proof? Well, this just would seem to be nice. Let me tell you a more specific version of this dream. Well, let me make a definition. Let X be a hypergraph. We say a hypergraph A is a KQR omni-absorber for X if for every KQR divisible subgraph L of X, you can find a decomposition of L union A. So absorber was decomposed 1N. An omni-absorber, omni meaning all, wants to be able to decompose all possible leftovers inside of X. So this is what I hinted at. So question, audience, do these exist? And the answer is yes, I told you this already. Given that KQR absorbers exist, you can do this private absorber trick, embed them vertex disjointly, and they will be able to decompose all possible leftovers. So you only turn on the one that you need to decompose L, and you leave all the others off. And this can decompose. But there's a problem with this. The previous construction has size 2 to the omega of x to the r, right? It's exponential size, because there's exponentially many possible leftovers. This is why they needed to get x down to be something like constant or really polylogarithmic size in order to embed all these absorbers. So this brings me towards dream number 2. Could it be true that there exist KQR omni-absorbers with size polynomial in X? This is kind of magical. I'm going to take care of exponentially many leftovers with only a polynomial size. Seems like a wild dream. Let's make it even wilder. Could you do it with size linear in X? Does this seem possible? Almost as efficient as possible. Well, this seems crazy. Well, we did it. So here's the theorem with Michelle. We showed that for q greater than r greater than 1, there's some c greater than or equal to 1, such that the following holds. I give you x, some subgraph of k and r, and what is size? It turns out you shouldn't count the number of edges, you should count something called the maximum degree. And what is maximum degree? In a hypergraph, it's the r minus 1 degree. So for every r minus 1 set, what's the maximum number of edges? And that is the right notion you want. So for graphs, that accords with their normal max degree. So if I tell you the maximum degree is at most n over c, so it's not too dense anywhere, but still could be like linear dense, and we let delta be the maximum of delta of x, and sort of this number, n to the 1 minus 1 over r times some log n, and that's just to account for the case where x could be very sparse. Then we can generate a KQR omni-absorber A inside K and R for x, whose max degree is at most c times delta. So what is this saying is, as long as delta of x is at least this number, I'm getting a linear efficiency here. Otherwise, it's sort of natural. So when when x is sort of sparse, it's not clear to us that this theorem would hold true. So this actually seems rather sort of the natural bound for us. So again, in other words, we show that linearly efficient omni-absorbers exist, again, provided x is dense enough. Okay. Well, what does that do? Well, now, assuming that theorem, whose proof I will talk about in a bit, I can give you our new proof of existence. I will fit it on one slide. So here is the outline for our new proof of existence. You only need like 4 steps. None of these are that complicated, but I'll go through them. Step number 1, random reserve. You're going to choose a subset X of all the edges uniformly at random with some small probability P that you can choose. And here you can choose P actually to be constant if you want, some small enough constant. You could choose it much smaller, it would also work. So this is not doing anything, it's just randomly reserving some edges, and we use Chernoff bounds to say that this acts as expected. Then we use our omni-absorber theorem. So by our theorem, again, since P is small enough, the max degree is small, there exists an omni-absorber with good linear efficiency. Then, unfortunately, we do have to do regularity boosting. But again, I said that we're just going to use theirs. They do it in 2 or 3 pages. It's clever, but it's not too long, and it's ultimately not too complicated. So what does that mean is you're going to, by deleting x and a, the complete graph is obviously very regular. Everybody's in the same number of cliques. But by deleting x and a, and we didn't really control that well, there's some irregularity. Now we'll just sort of use their lemma, which says you can find a subset of the cliques that's even more regular than it was before. And with that, you can apply nibble. So technically, you apply what we call nibble with reserves. So that's, you run nibble, that almost decomposes everything outside x union a, and then you use this random reserve, like I did in that cover down picture, just that first step, to put all the edges into cliques whose other edges are in the random reserve. So that'll push all the leftover into x. And then the finish is, there's not a step, it's just true. You're done. So why are you done is K and R is assumed to be divisible. The packing, KQR, packing Q, is divisible because it's a decomposition. A is divisible because if you use the empty leftover, it has a decomposition. So if you put all that together, it tells you your leftover has to be divisible. And then by the definition of omniabsorber, A union L has some decomposition, call it Q prime, Q and Q prime together, give you your total decomposition as desired. So this is sort of this is what we mean by assuming the omniabsorber theorem is sort of one sort of step of absorbing. You're just using it right here once. Right, so of course you still need to use nibble, but now that's more standard and known. You need the regularity boosting. And the random reserves, I mean, that's just easy. So this is our proof of existence. Yeah?
So for the omni-absorbers, for instance, if you had quadratic bounds, would you have done this twice?
So yeah, if you had a quadratic, yeah, so this is a good question so this is what's called an edge vortex. So instead of picking vertex subsets random, we're picking one edge set. So you can make what's called an edge vortex, which you pick a subset of edges, inside you pick a subset of edges, and so on. The issue is that wasn't able to be done before because you would need sort of at least quadratic efficiency. You'd actually need slightly better than that, like in the triangle case. Because it turns out if you take a random subset of edges that's too sparse, they're just not going to be like any triangles inside of it. So basically that was our original plan, but our things are so efficient you only need one level of edge vortex. You only need one choice. But you could have done this a bit, but you can't do it forever like they do for vertex vortices. So this is the trade-off. It's like the natural thing to do is this edge vortex, but nobody knew how to do it because you didn't have access to these very efficient absorbers. But a very good question. Okay. So how are we going to prove the refined omniabsorber theorem? That's the thing. You have maybe convinced you we could do existence if we had this, and indeed that's the point. The existence proof is only some number of pages. The rest of our, almost 40-page paper is trying to prove this theorem. So how do we prove it? Well, let me tell you about an even crazier dream. I said there were 3 dreams, right? Well, to that, let me make a definition to formalize this. So I have an omniabsorber A for x. I'm going to label parts of it. So one thing I'm going to call a decomposition function QA, and I'm going to talk about a decomposition family H. What are these is, well, I told you for every KQR divisible L, there was some decomposition of L union A. I'm just going to fix that as a function. So there could be many decompositions. Fix one, call that QA of L. And I'm going to fix the set of cliques you're allowed to use in the decompositions. Call that the decomposition family. So you're promising that Q of A of L has to be inside this family of cliques H. So sort of H is the support of L in the QA in the cliques. So you might think this is silly because why wouldn't you just use all the cliques, right? Like you're allowed to, freedom, and then H is everything, and okay, you could fix a function, but is that so interesting? Well, here's the secret. Don't use all the cliques. Don't use them all. You're way too wasteful. So here's a definition, C refined. We'll say a KQR omniabsorber A for x is C refined if for every edge E of A union x, the number of elements of H, your decomposition family, that contain E is at most this constant C. So this is just a definition, doesn't say anything. But if C is some constant, we're saying our family, every edge is only in constantly many cliques. And so now you can maybe imagine dream number 3. Can we find linearly efficient omniabsorbers that are C refined for some constant C depending only on Q and R? So not only do I want linearly efficient ones, I want you to use very few cliques. Every edge is only in a constant number of possible cliques, and only with those I can decompose every possible leftover in a linearly efficient way. This seems crazy. Well, we did it. That's this line. So same theorem as before, just with the word C refined added. So we can actually find these C refined omniabsorbers with linear efficiency. And now I should ask, why is C refined useful? So I gave you a proof of existence that didn't require things to be C refined. So why is it useful? Well, it turns out the proof of this theorem will run by induction on the uniformity. And having C refined is key to making the induction work. So when we want to use these inductively to build larger ones, higher uniformity, having that C refined, knowing that you weren't sloppy in the lower uniformities, will allow me to power it. And so then we need it to go inductively. Secondly, is that C refined provides a template for designs in other settings. So this is just the existence conjecture. But maybe you want to do high girth. Maybe you want to do minimum degree. Maybe you want to do in random. There's tons of other settings of design theory. And the point of this is it gives you a template. What do I mean is it sort of gives you a plan of cliques to divide everything into in a very nice refined way. And like maybe those cliques aren't in the host graph that you want. But maybe you could say, well, maybe I can re-embed them somehow into a random graph or into a min degree graph. Sort of use this approach. So it gives you a nice template. And once you have that, it turns out this template is actually a key to our other applications. So I'll mention at the end of the talk some other applications we have. Really, this is a series of papers. The latter one's also joint with Tom Kelly, who's here, where we use this to solve new problems. This is a reproof, but we're going to use it. And the point of this is the above theorem is a black box theorem. We're going to use it as a black box, and it never needs to be reproved. So cover down, it turns out you have to keep redoing it specifically to every individual setting again and again. Here, we can do most of the work in this black box theorem, and then you do a bit more to apply it to your different settings. But at least you don't have to redo this 20 pages or 30 pages or so. So again, I like black box theorems, so I think this is very nice. But I haven't really told you how we do it. So let me tell you about the one uniform case. An NQI1 Steiner system, that's the one uniform case. What is it? It's a partition of singletons into Q sets, right? R is 1, so those are singletons. You're going to partition them into Q sets. So a set G is KQ1 divisible. You could check the definitions if and only if Q divides the number of elements of G. So fact, if you're KQ1 divisible, you all know this fact, you have a KQ1 decomposition. You can divide a set whose multiple of Q into Q sets, yes? You just do it. Number theory, check. So this is why the existence conjecture is normally not stated for article 1, because it's trivial. What else is trivial? Well, what about absorbers? Maybe absorbers are interesting. Well, actually, the above implies that for every divisible thing, there exists an absorber, the empty one. So even absorbers aren't necessary, they're empty. The empty one works. What about omni-absorbers? Well, the empty one still works. But is the empty one C refined? Is there anyone? You think about, right? No. It's not refined. So why? Just think of the K21 case. You'd want to divide things into pairs. If I give you a giant set and I put the empty absorber, I don't do anything, then this is not C refined. Why? Well, it could be that the leftover is any pair among my giant set, and I'm telling that pair they have to be together. So ergo, I'd have to be in a pair in the family with everyone, which is linear size, not constant. So it's like, what we'd want to do is somehow be able to pair things up where you only ended up with constantly many possible friends in this pairing. So let's look at this more. What is a C-refined KQ1 omni-absorber for set X? What does it mean, and can we build it? Well, it has a nice alternate interpretation with hypergraphs. So it's equivalent to the following, actually. It's equivalent to finding a Q-uniform hypergraph, H. H will be the decomposition family, viewed as a K-uniform hypergraph, whose vertex set is A union X. The C-refined property converts to max degree of H being at most C, with the property that for every L subset of X, that where Q divides L, you can find what's called a perfect matching of L union A in H. Matchings are the one uniform equivalent of decompositions. And are these known to exist? Well, in a breakthrough result, Montgomery in 2019 proved that these things exist in a related but much harder setting, which is the Q-partite setting. So can you do this sort of in bipartite graphs, for example, or generally Q-partite Q-uniform graphs to have sort of robustly matchable hypergraphs? But we don't actually need that, and it's not clear the partite implies it for all that we need. So I'll just give you an easier construction. Here it is, and there'll be a picture in a second. So what are we going to do? We're going to have A be Q times the size of X. And then it turns out we're going to combine two things. We're going to take what's called a tight Q path with vertex at A, and a tight Q path on X union A, where we insert the vertices of X after every Qth vertex of H1, and H will just be the union. So what is a tight path? I want to find it. I'll just give you a picture. So for Q equal 3, x equal 3, A would be 9. Here are my 9 A vertices. Here's a tight 9 path. So it's just sort of, in higher uniformity, you have to say how paths work, and tight means they have as most overlap as possible. So you overlap in all but one. So here's a tight 9 path. Tight 3 path, but sorry, on 9 vertices. And here is it with x stuck in. So do the same thing, but I said put x every third vertex. And here's the tight 3 path on 12 vertices. And the union of the two is the thing you want. So if you delete any vertices of x, they're far enough apart that it turns out you still get a tight path on whatever remains. Sort of you combine these edges, and then you sneak down and use those ones if you want to pick up things of x. And the point is, tight paths naturally just have decompositions if they're divisible, because you just take the first 3, the next 3, and so on, and that's how you do it. And this even has the added nice property that even if you weren't divisible, it would sort of only leave a couple at the end. And I'll use that property later. But for now, this does what you want. So that's the one uniform case. So we've proved the one uniform case of our omni-absorber theorem. It was mildly interesting. Here was this nice construction. So how do we do it in general? Well, we needed an idea called refiners. And this is really what drives everything. And the question is, can we make our job easier by finding something weaker first? Right? So we've made our dreams really wild. Let's make it a little bit easier. What's the idea? Well, it's the same as an omni-absorber for one difference. So we're going to have an R. It's going to be called a refiner. It's going to have a refinement family, a refinement function. The only difference is instead of decomposing into cliques, I want to refine into KQR divisible subgraphs. So instead of decomposing into cliques, which are divisible, I mean they're decomposable, let me just get like small divisible things. But of course, the empty hypergraph is trivially a KQR refiner. If I have something that's divisible, it's divisible, so I didn't do anything. So currently I haven't done anything. So we demand more, which I just hinted at. Here's how we demand more. We'll say a KQR refiner is C refined if it has that refined property, so every edge is only in constantly many things, constantly members of H. And since we're no longer doing cliques, I'm going to impose that the size of H is bounded, so say at most C. So I want to break into constant size divisible things, each edge is only in constantly many of them. So this will be a C refined refiner. So we will prove the C refined refiner theorem first. And this actually implies a refined omni-absorber theorem with a simple trick. Here it is. We use this refiner as a template. What's the issue is now you've decomposed into small divisible things. But if we assume absorbers, for everything in your refinement family, you can embed a private absorber for that little graph. It's little. These absorbers are little. It takes some work because you have to do this inside a spanning thing. So you have to make sure these are all, they can't even be vertex joint. You have to make them edge disjoint. So that's some work to do that, but we do it. And so the key is to show it's edge disjointly, and you also want to make sure it's low max degree as well, right? Because we needed the whole thing to be low max degree. But let me skip those details. Now we've reduced our work to, we just need to refine into small divisible things. So we make another reduction. It actually behooved us to first prove these theorems in the setting of what's called multi-hypergraphs. What is a multi-hypergraph? It's a multi-set of subsets. So basically parallel edges are allowed, but I'm still going to be uniform, so I don't allow loops, like you're not allowed to have vertices multiple times in an edge. And we'll actually prove the multi-refiner theorem. So where R and X are allowed to be multi-hypergraphs. And we can similarly define, from this embedding absorbers, you can derive a refined multi-omni-absorber theorem. That's that. What's the difference between this multi-setting and not is they don't imply each other. The multi-version is both easier and harder. So it's easier because A and R, the thing your absorber refining, is allowed to be a multi-hypergraph. That seems easier. However, I said X could be a multi-hypergraph, so that's harder. Also, I should point out we no longer need to assume in this setting, say that delta of x is the most n over c, because I'm allowed multi-hypergraphs, I'm allowed multiple edges, so I could have degree more than n, for example. But the claim is that the multi-refiner theorem implies the refiner theorem. How do you do this? It's nice, we replace every edge of R with what we call a fake edge. What's a fake edge? Well, here's an anti-edge. You take a clique and you delete an edge. That turns out has the negative divisibility properties of an edge. You have like a hole there, everything's sort of -1 in divisibility. If I repeat this construction where I take an anti-edge and replace all of its edges with anti-edges, you get what we call a fake edge. So it turns the negative into a positive and has the same divisibility properties as an edge. And importantly, it didn't use the edge. So this means that if we embed the fake edges disjointly wherever you wanted a multi-edge, and you do it with low max degree, you'll have the same divisibility properties. In particular, so you've upped the size of your refinement family a bit, but they're still small divisible things, and you run it back through absorbers. One other key to proving the multi-refiner theorem is we don't prove it all at once, but rather we allow what's called a remainder. What's a remainder is, I just promise that I refine not all the edges, but sort of all the edges that are outside of what's called the remainder x prime. So this begins to look analysis to cover down, but in sort of refining, like I leave some remainder of unrefined edges. And the key is we can actually always force remainders of what's called bounded multiplicity. Namely, you could take the least common multiple of all your divisibility conditions, we call that MQR, and it turns out a nice fact is that MQR parallel edges are KQR divisible, because they have the multiples you want. So how do you reduce multiplicity? Say to, at most this number, is you would take a bundle of parallel edges x and view it as a one uniform hypergraph. Well, anything more than MQR, you can kind of make into bundles that are divisible, except I need it to be refined. But the idea is you'll add a K1 MQR omniabsorber R of new parallel edges, and those promise you can always, in a refined way, break it into sets of size MQR, which would then be these small divisible things. So that's sort of a key for us, is this multiplicity reduction. And importantly, like the remainder always lives in the first MQRs. So that's the bound multiplicity. So then I can tell you what refined down is. So again, there'll just be a picture ultimately, but here is the high level steps before the picture. So we're going to do the cover down, but for refining. So we're going to build a vertex vortex, V0 down to VK, and we're going to try to push the remainder all the way down to VK. And once we get it to VK, which has constant size, you basically get to stop, because anything that's divisible of constant size, you could just sort of imagine adding it to your refinement family. And it'll be refined. So how do you do this? Well, for each edge, that's here you're not decomposing everything, but you're refining the things in X. So the things in X that don't have any vertices in VI plus 1, you turns out you randomly choose a private clique as the refiner. And then you sort of do, for all the edges of intermediate size, you do this induction on uniformity, where you use what's called a local refiner of a smaller uniformity. And so embedding it randomly keeps things low max degree. Also, you don't have to worry about disjointness here, because we allow multigraphs. It's nice. And as I said, once this is constant, sort of the empty one should do what you want. What's a local refiner? Well, here's the definition. It's mostly if I was looking at an X, and I tell you every L subset of X, and I tell you I'm looking at the link graph of S, then if it's divisible, then I'm claiming you can get a decomposition of it. So sort of if you have divisibility lower, I want a decomposition higher. And what's known is if you are divisible, then your link graphs are divisible. They use this in both the other proofs. It's sort of the simple algebraic fact you want. And the key is by induction on uniformity, we can sort of find an omniabsorber one lower that's refined. And then we just sort of, we have to add it, but you have to be a little bit careful in adding the correct number of edges to keep divisibility. So let me do a picture of this. Here's this triangle picture again. What's the differences? We have some edges of X here in blue. So instead of like nibbling and getting rid of most, we just have some sparse set of edges in X. I need to refine them. So I embed them in a private triangle, each to the vertex. So this has refined them. They're only in one triangle, check. I don't worry about them. They might not be present, but we've done that. But now the issue is I get rid of those, but those edges maybe don't end up in that triangle if the blue ones didn't, so I need to refine them. And there could have been other blue edges from this vertex down that I also need to refine. So they become sort of a new remainder after the first step. And so we refine them, say at a vertex V. And so before we just put a perfect matching in, here's what you do here, is you put this lower omni-absorber in. So in this case, I do the threading technique, right? I take a tight path, and then I insert the vertices and put a tight path. So tight paths in graph is just paths. And then the point is, this should be able to decompose anything, any of these edges into matchings, and i.e. into triangles. There'll be some remainder left in here, but that's what we want. I just have to be careful to get the divisibility right. You see the red stuff I added is not triangle divisible, because the vertices on the end, for example, have odd degree. So the trick is that you fix one decomposition with these red edges. So like look at those triangles. And then all the green ones, all the other red edges, I will add like 6 parallel copies to just make sure they're triangle divisible. And that's the idea. So in my remaining time, let me just talk about further applications. So yeah, we did refine down, mimicking cover down, but it's a different flavor because you're not covering, you're refining. But similar ideas. And it's hard, but we use we use multiplicity reduction here to reduce the multiplicity once we're done, because maybe get many parallel edges is another point. And we use induction, what? Yeah. And we use induction on the uniformity, because this, you can only add this in a way if the thing below is C-refined, as it turns out, because you only want to add enough of these types of edges you put into the cliques one lower. But anyway, so further applications.
Before you move on that picture, can I see something?
Yeah.
So the property of this red tight pad is that if you remove some of these blue ones, you will be able to match?
Yeah, so whatever blue ones you remove, but it has to be divisible, right? So you need to remove an even number of them. It was the assumption, right? You give me a divisible subgraph of blue. So there will be, maybe you have just these two, and then you'll match this, and you'll match, maybe I didn't put in, maybe you should put in a couple extra edges, maybe I lied. But
the property is that if you remove any even number of blue edges, the rest is matchable.
Yeah, the one from before, but maybe I cheated a little bit because of the sizes, but yeah. Maybe here you could just put in some extra ones. But I think the other one I did 2 times the number of x, so yeah, good point. Further applications. So I'll just mention them briefly. So we had 3 further applications. Mainly we released a set of 4 papers at once. So Michelle and I did that in the first one. Michelle and I proved what's called the high girth existence conjecture second. And then with Tom, we studied clique decompositions and random graphs, also with Tom and Michelle, I mean. And then we also looked at thresholds. So our first paper was 40 pages, and this one's like 20, like 18. This one's like 50, and this one's like 56. So it's a lot. So obviously I don't have time to tell you all of these things in one talk, but I will give you one quick slide about each, just so you can understand what the applications are. So what is it? Well, if you like random graphs, GMP, here was an old conjecture of Euster that said, if p is at least sort of this number, this threshold, then asymptotically almost surely GMP should have a KQ packing covering all but at most QN edges. And it turns out the reason is because this is sort of the number when things are in at least one clique. So that's sort of that's why it's the conjecture lower bound. And what's the point of all but at most is, well, GNP might not be divisible. So for example, if you're doing triangle decompositions, you'll have odd degrees. You can't perfectly cover it, but maybe you can cover all but a linear number. So Nibble would give you something subquadratic, but he wanted linear, which seemed quite hard. And basically nothing was known about this. No good bounds were known, maybe some n to the minus epsilon for some very, very small epsilon. But what did we prove? We basically almost got there. So for here, when Q is 3, for triangles it's a half, and we got to a third. In general, it's 2 over Q. We got to sort of 1 over Q. And we even can cover with more edges, fewer edges, as it turns out. And we even did the same for random regular graphs, where D is equal to Pn is the appropriate number. And that used results in the sandwich conjecture by our own Jane Gao, Isayef, and McKay. to kind of reduce it back to the GNP with some additional ideas. So I won't get into that, but I thought this is very, very nice. Another one that's nice is the binomial Q-uniform random hypergraph, GQNP. So there was this conjecture by Kang, Kelly, Kühn, Mathuku, and Osthus that said if P is at least n to the minus Q plus R log n, then asymptotically almost surely GQNP contains an NQR Steiner system. So the idea here is, what if I want you to build a Steiner system, but I don't let you use like all the triangles or all the Q cliques? I only randomly pick a subset of Q cliques, and you have to build it from that. What's the threshold to contain? They said this should be the right number, because it turns out that's the probability that every edge is in at least one of these Q cliques. And for R equals 1, this is actually a famous problem about perfect matchings, the threshold in Q-uniform hypergraphs, settled by Johansen, Kim, and Vu in 2008. It won them the Fulkerson Prize, actually. For Q equal 3 and R equal 2, there was all this work in 2022. So Sawsani and Simpkin showed n to the minus 1 plus little 1. They showed n minus 1 log squared n. And then Keevash and independently James and Fan, building on this paper, were able to fully resolve the conjecture. Up to the constant, of course. I mean, there should be like a constant there, OF, but sure. But they only were able to do the triangle case, and it didn't seem like any of the methods would generalize to higher Q. But with our new techniques, we can do for all Q, but R equal 2, n to the minus Q plus 6 over 2. So instead of the Q, you're kind of getting Q over 2. But still pretty good. And the last one I talked about in the fall was this high girth designs. So the girth of a Steiner system is the smallest integer, so you contain what's called a configuration. It's basically a set of K subsets, KQ sets on at most this number of vertices. That's not really important. The important thing is conjectured by Erdős that sort of Steiner systems of large girth should exist. So he particularly said triple systems should exist. So in 1973, he wanted to know this. And, this is just about Kirkman things, right? Just something we've known since mid-1800s that Steiner triple systems exist. And he wanted to know, do high girth ones exist? And it had a long history, but the approximate version, so the Rodel type of result, was settled independently by these two groups, Glock, Kühn, Osthus, and Bowman-Warnke, in 2019, almost 50 years later. Actually, the full conjecture was just proven 2 years ago, which is where Michelle and I got interested in these things. By Kwon, Sawsani, and Simpkin, they showed that Erdős's conjecture is true. So it took 50 years to prove this conjecture. It took 150 years to prove the existence conjecture. But Glock, Kühn, and Osthus, and also by Keevash and Long, reiterated what I'll call the high girth existence conjecture, that for sufficiently large n, you can find NQR Steiner systems of girth at least G whenever it's missed. So you can find high girth. So this commonly generalizes both the existence conjecture and Erdős's. So I don't know if you take 150 and 50 and you should add them or you should product them, but this seems hard. Well, the approximate version, though, was settled by Michelle and I talked about that in the fall in 2022, still not published yet. Glock, Yost, Kühn, Kim, and Lichev in 2022, independent proof. And now with our method of refined absorption, Michelle and I can prove that the high girth existence conjecture is true. So really 2 plus 10 is this here. And now we're done. So we've provided a new proof of the existence conjecture via the method of refined absorption. We proved this refined omni-absorber theorem that can be used as a black box template going forward. So these are just the applications we most knew and care about, but there could be many, many more in many other settings as well. And we discussed some of these further applications, so if I had more time, or maybe I'll give another talk later and we'll go through, talk about the proof, but just to give you the highlights. Thank you.
Thanks a lot for the talk. Are there any questions?
Hi. So for you proved the existence of linearly efficient omni-absorber, and you've got a limit on the density of X. And if you manage to go lower than that, would that be useful for some application?
So it turned out, well, originally we had it not linear, but almost linear. And it gave some worse numbers, so it only worked maybe 1 over r squared. But we decided to work harder because actually for that GNP one, 1 over r squared is a quarter, and we wanted to get down to half. And so our number there, the absorbers would work down to half, and we only get to a third for other reasons.
Yeah.
But sort of 1 minus 1 over r is sort of better than in all the conjectures that you would actually want. So it doesn't seem like, and it's not clear to me it's true below that, because it's hard to imagine that you could have a very sparse thing, say constant degree, and hope to build a linearly efficient omni-absorber of all the things. Not that I don't know a counterexample, but my gut is that this is maybe around best possible.
And so to get, there's still a gap between Euster conjecture and what you managed to prove. So to kind of get a better bound.
Yeah, so what we show, because we did work on the third, is the issue is absorbers. So it just turns out sort of the sparsest absorbers we can build are of that, and we tried really hard to build them as sparsely as possible, and we can prove you can't really build them sparser. So if you want to use the method, at least of like constant size absorbers, maybe you can save a little bit if you allow really large ones, but then you have to be careful because you have to embed them out into space and blah. But morally, it seems like a lot of the point of this work is we can reduce a lot of these problems, even in the random setting or high girth or so on, down to sort of absorber thresholds. And that tells you if you want to use absorbers as your main technique, like you need to either build better ones, but in a lot of places we can prove, and you can't really do much better in the constructions. And so then maybe these conjectures just aren't true and we're not good at building constructions. So.
Thanks.
Any further questions? I have one. I don't know. It's probably silly, but I'm still. So at the moment you're covering complete R complete R hypergraph with those clicks. I wonder, is there something that considers packing covering that with other maybe highly symmetric graphs where those
Yes, that's a good question. So we talked about in random. There's this min degree version, so if you assume everything, you're almost complete. And there's famous conjectures, even in the graph case of Nash-Williams on what's the number for a triangle. So the conjecture there is 3/4 n. Michelle and I have the best number of 0.827 in an earlier paper. But they've sort of tied the integral to the fractional in those settings. But yes, I should have mentioned that Keevash and Glock, Kühn, Osthus can do some things in what are called typical, which are sort of like quasi-random. So if every set of vertices is in sort of the same number, so this high symmetry you're going after. But they still, so Glock, Kühn, Osthus still need sort of constant proportion of density, so some linear number, and Keevash still needs it to be at least n to the 1 minus epsilon or so dense. So you can't do it for at least their methods don't work for symmetric things that are way too sparse, but symmetric or quasi-random looking things that are very dense. Admit these decompositions, assuming they're divisible.
What is divisibility? What is divisibility?
Oh, it's this K. I defined this KQR divisibility more generally. So you look at the link graphs.
Okay.
So for a graph, to be triangle divisible just means every vertex has even degree, and the number of edges is divisible by 3. It's sort of the obvious thing that you would need to be true. And so you can make this work in not complete settings. And again, that's what we're doing. We're building absorbers. We're of some x. So you can arguably try to apply it for all those different kinds of problems, but maybe you need, more things to make them work.
Thanks. Are there any final questions? Otherwise, we will take everything offline, and people are okay. So then we take everything offline, and people are happy to organize themselves to go to Great House. Thanks.